to the third part of the paper, and we're on now to question 18. And we've got a ester to work out the name of. So when we're working out the names of esters, we're going to just see which bits come from the alcohol, and that is this bit, and then which bit comes from the acid, and that's this bit. Right, and in the name of an ester, the alcohol comes first, so we've got 2 carbons in our alcohol, so we're going to have ethyl. And looking therefore at the acid, alright, we've got 3 carbons, and we've got a bromine on the 3rd carbon, so if this is carbon number 1, carbon number 2, carbon number 3, so it's going to be 3 bromo. And then we said we had 3 carbons, so it's going to be propanoic acid, propanoate. So ethyl 3-bromopropanoate is the name of that acid, and you write that down there for the mark. So part 2, we've got 4 boxes to fill in. We have to draw the organic products of these reactions. Okay, so we've got, this is clearly hydrolysis, acid hydrolysis. Alright, so we've got acid hydrolysis here and base hydrolysis. A downward arrow. Alright, so let's just, so that's, where is it going to break? It's going to break here. So that's going to be the acid, right, and using the colours the wrong way around, sorry, that's going to be the alcohol. Alright, so let's just draw in our alcohol. Alcohol is not changed whether it's acid or alkali hydrolysis, so we're just going to give that oxygen back its hydrogen from the acid, and so we've got ethanol there. Okay, now in terms of the acid, just try and squeeze it in the corner here. Alright, we're going to remake the acid, and it's going to be protonated because it's acid hydrolysis, and we're going to have our bromine on the end there, like so. So we've got 3-bromo propanoic acid there. Okay, so going down in this direction now. Again, we can remake our acid, and this time we're going to deprotonate. Right, so we're going to, the hydroxide is going to rip off this proton from our acidic proton there, so it's going to remain like that, and we're also going to get something else happening here. So our hydroxide is going to attack this delta positive carbon here, and we're going to get a bit of nucleophilic substitution going on, so we're going to have an alcohol end to that molecule there, like so. Okay, so that's that one, and then the ethanol is just like it was before. Okay, so there are our 4 products, and we have to name the type of reactions. Well, let's, we've named it already. They're hydrolysis reactions. Okay, we've got a little bit of NMR happening in part B, and so we've got our ester A in the diagram there, and they've kindly isolated all our hydrogen environments for us, 1, 2, 3 and 4, and we have to complete this table here, which is chemical shift, just a matter of finding the right place in your data sheet. Right, so you'll find that environment number 1 is going to be a shift of 3 to 4.3. And the splitting pattern depends on the adjacent hydrogens. So these are the adjacent hydrogens, and there's 2 of them. All right. So let me just write our n+1 rule here. So the hydrogens that are on adjacent carbon, call them adjacent hydrogens, +1 is the number of peaks. All right. And so if we've got 2 adjacent hydrogens, 2 plus 1 equals 3. So we've got a triplet. All right. So we're going to put a triplet in here. Here. So then let's have a look at environment number 2. All right. So it's next to a carbonyl carbon, and we find that, and we're going to give that a shift of 2 to 3. Right, and its adjacent hydrogens are on the left. They're the hydrogens that are in environment 1. And there's 2 of them, right? So that's a triplet as well. Okay, so let's do environment number 3. So that's adjacent to an oxygen, single bond oxygen. And so that's quite a high shift, 3 to 4.3 again. And its adjacent hydrogens are these 3 here on the end. All right, so 3 plus 1 is 4, so it's a quartet. All right, and that leaves the environment number 4, whereby it's just next to it's a long way away from the oxygen. So it's got a lower shift, so it's 0.5 to 1.9. Let's choose a better colour. And its adjacent hydrogens are these 2 here. Alright, so 2 plus 1 is 3, so it's a triplet as well. So there we have it, 4 marks. So now in part C, we're introducing this compound B, which is a structural isomer of ester A. And remember what a structural isomer is. It's got the same molecular formula. Different structural formula. All right, so it's going to have the different functional groups. And it says it reacts with aqueous sodium carbonate, right? So that means it could be an acid. Right, and we've got 4 different environments, although it looks like we've got 5 carbons. 1, 2, 3, 4, 5. So we're going to have 5 carbons. All right, 5 carbons, 4 environments. So 2 of our carbons need to be in the same environment. So first of all, let's draw out our acid. So it's going to be one end of the molecule. Let's draw it structural. And we want 5 carbons in total, 1 of which we've drawn, and 2 of which are in the same environment. So we could have 1, 2, that's 3, 4, 5, and we need to add a bromine on. Let's put the bromine here, just check that. So we've got 1, 2, 3, it's not going to work, so let's put another carbon on, put the bromine on there. So we've got 1, 2, 3, 4, 5 carbons, 2 of which are in the same environment. That's the 2 methyl groups hanging off carbon number 2. And we've got the same molecular formula, so I think that works. Of course, there are alternatives. So we could have our 2 methyl groups on carbon number 3. So if I could draw, I'll just draw that out for you. So we've got our acid group, just the same one. We could have our methyl groups coming off carbon number 3 instead. That works. Or we could move our bromine. All right, so if I draw it down bottom left, we could have bromine coming off carbon number 2. 1, 2, 3, 4, 5. We've got 5 carbons there, and 2 of which are in the same environment. So either of those, any of those 3, get however many marks there are for that. So moving on to part D, where we're getting a polyester formed from 200 molecules of 4-hydroxybenzoic acid. So if we draw out 4-hydroxybenzoic acid so we can work out what's happening. So we've got a bit of benzene. Let's have our acid group coming off this carbon. Right, which means our hydroxyl group's coming off here. Right, and if we were to polymerize that, or make the polymer out of it, let's draw our repeating unit. So we've got let's draw it just a bit horizontal like this. So we're going to have right, so let's draw our brackets here and here. Right, so we've made a polymer out of 2 units here. So first of all, we need to think what's the MR of 200 molecules of 4-hydroxybenzoic acid. So the formula of 4-hydroxybenzoic acid is, let's count the carbons. We've got 7 carbons, and we've got 6 hydrogens, and we've got 3 oxygens. Right, so that MR of that is going to be 84 plus 6 plus 48 is 138. Right, and each time we get an ester link, all right, we're going to drop out a water molecule. All right, so that's minus 1 water molecule here. Right, and that's going to happen 200 times. Or is it? Right, because the end molecule is going to, let me change colour, the end molecule is going to have 1 unreacted acid group, right, and 1 unreacted alcohol group on the other end. Right, so that unreacted acid hydroxyl group of the acid and that unreacted hydroxyl group of the alcohol makes 1 water molecule. Right, so you're actually dropping out 199 water molecules, condensing out 199 water molecules condense. Okay, so once we've appreciated that, then we can work out the MR of the polymer, of the polyester. Right, it's going to be 200 times the MR of the 4-hydroxybenzoic acid, which is 200 times 138, minus the 199 molecules of water that condense out, each of which has an MR of 18. All right, so the MR of the polyester is 24,018. Like so. Okay, here in part E, we've got a synthesis question, and we're going to try and synthesize this ester C. All right, it's 2 stages. Right, and we've got a certain mass of, we've got to make a certain mass of this ester, and we're starting from an aldehyde. So we're starting from an aldehyde. Alright, and we've got a yield of 40%, so we're only getting 40% of what we would have got if the yield had been 100%. Right, and we need to, for each of the 2 stages, we need to give reagents, conditions, and equations. Okay, so as is usual with synthesis questions, it's good to start at the ends. All right, so let's write down our finished product, our ester. So we're just going to copy it from the question into the right hand side over here. So we've got CH3 So there we have our ester, and then we can just remind ourselves that we usually make an ester from an acid and alcohol, and this bit here is going to come from our alcohol, and let's say this bit here is going to come from our acid. Yeah, so what alcohol we're going to need? Well, that is methanol. Methanol's going to give us that bit of the ester. And what acid are we going to need? Well, we've got 3 carbons and a methyl group, so we're going to have methyl propanoic acid. Methyl propanoic acid don't have to write the 2 because there's the only place it could go. All right, so that's what we're going to need. So let's just write out a little equation. So we're going to start with our methyl propanoic acid. There's our methyl propanoic acid, and here's our methanol. All right, we're going to react them together, and under what conditions? Well, we need an acid catalyst, don't we? All right, so acid catalyst, usually here sulfuric acid, and we need heat, usually provided by reflux. Okay, so we've got our methanol would be a reagent, all right? So as well as our methyl propanoic acid. So we've got reagent and conditions for the second step. So let's just call this stage 2. Right, because we might want to write it out a bit neatly in text as well. And so that's not what we start with. So let's go over to the left now and write out what we start with. All right, so we start with the aldehyde. All right, so we've got methyl propanol. Okay, so there's probe, methyl propanol, yeah. So 2-methyl propanol. So there's 2-methyl bit, and there's our propanol. So that's what we've got to start with, and we want to make it into an acid. All right, so we have to remember that we're going to add oxygen. We don't need the mechanism, so we can just call it oxygen in square brackets, and we're going to turn that into our acid, our methyl propanoic acid. How do we do that? Well, we do that with acidified dichromate, but notice it says reagent, all right, so we need potassium dichromate. We can't just write out dichromate. So we need potassium dichromate, and it needs to be acidified, and we reflux that. So we've got reagents and conditions, and sort of equation there for that. Right, so that looks pretty good. Let's call this stage 1. All right, and what I would recommend is, as well as that, on your exam sheet, you would just write out in text stage 1. You'd give reagents, conditions, and write out the equation for both stage 1 and stage 2. But we've got the basis of it there, the little plan of it there. Now let's calculate the mass that we want. All right, so we need the mass of 2-methylpropanol required, and we're going to start with we're going to start our calculation with the 12.75 grams of ester that we make. Okay, so we're going to do it with moles. Okay, so we're going to work out the moles of our ester C, we're going to need the MR of ester C first. Right, so we're going to work out our MR, counting all the carbons and oxygens, hydrogens. It comes up to 102. Right, so therefore we can work out our moles that we've made, the actual moles that we've made. So moles of C, right, actual is going to be our 12.7 grams, our mass, 12.75 grams, divided by 102, which is our MR, and that gives us 0.125 moles. 0.125 moles that we actually made. All right, but we've got yield. All right, so let's just, in a bit of scrap paper, you remind yourself that yield is the actual moles or mass divided by the theoretical moles or mass that you made times 100. So that's on a little bit of rough paper. All right, so now we can continue our calculation to work out the amount of aldehyde that we theoretically could have made, or the amount of C that we could have made. So moles of, let's call it moles C theoretical, is going to be, from that equation we can see that that's 0.125 over the 0.4 yield, and that comes at 0.3125. 3.3125 we could have made if we'd had 100% yield. Right, so using that number, then we can see that from our equations, it's a 1-to-1 ratio between the aldehyde and the final ester that we make. All right, so the moles of aldehyde, let's just change colour a little bit because I'm running out of space here. So the moles of the aldehyde, let's call it ALD, save us writing out 2-methylpropanol. Moles of the aldehyde is 1-to-1, so it's 0.3125. We've already taken account of the 40% yield only. All right, but the question is asking us for the mass. All right, so the mass of the aldehyde is going to be moles times MR, so it's 0.3125 times the MR of the aldehyde, right? So we work that out, and that comes out 72. All right, and that works out at 22.5 grams for the final mark. Okay, last part of this question is here with the last 2 marks, and we've got some fragmenting going on of ester C. We can see that here's our 102 molecular ion peak. All right, and we've got Z at 71, and we've got Y at 43. So we have to suggest possible structures for Y and Z. Okay, so if we have a look at our ester C molecule here, and if we had a look at what the MR of this bit is. And we could see 15, 15 is 30, 40 to 43, right? So you see that that bit's 43, right? And difference between 43 and 71 is 16, 28, right? And we've got 28, the carbon and oxygen is 28, all right? So if we imagined this bit of the molecule here, the MR of that is 71. Okay, so that means the structure of Y is going to be CH32, CH, all right, should have written this in red, right, but let's not forget we've knocked an electron off with our electron bombardment, so we need the plus charge there, and then we can put Z in here, so we can add carbon and oxygen in there. So we got CH32, CH, CO. Also we want the plus sign in there as well. And you can write the formula just like this, as long as you've got the plus sign in there. You can write out skeletal or displayed, whatever you like. Okay, this question 19 is about benzene, and we're looking at Kekulé versus delocalized. See our command word, we've got describe, but notice that we're going to describe in terms of the similarities and differences in the orbital overlap. So we don't want to just describe the Kekulé and then describe the delocalized. We have to phrase it in terms of similarities and differences as regards the orbital overlap. Okay, so I would suggest having a couple of subtitles, right? So similarities, and I'll leave you to put this into a proper full sentence, right? But they both make pi bonds by the overlap of p orbitals. That are perpendicular to the plane of the ring of carbon atoms. Right, so say something about perpendicular or sideways. Okay, so that's one similarity. Another similarity is that the pi bonds are both, pi bonds in both are above and below the ring of carbon atoms. Okay, so a couple of sentences there about similarities. Difference then, right, is that Kekulé has 3 alternating discrete pi bonds, whereas the delocalized model, the all overlapping pi bonds, overlapping p orbitals are spread out, right? All overlapping p orbitals are spread out into a ring both above and below the ring, the ring of carbon atoms. Okay, so that should get you 3 marks for that A part 1. And A part 2 is about the experimental evidence that leads us to work with the delocalized model rather than Kekulé. All right, so and you just asked for 2 pieces of evidence. All right, so probably the easiest to talk about is the carbon-carbon bond length. is shown to be the same, whereas Kekulé would predict that double bond to be shorter than a single bond. Okay, so you finish that sentence, and another one would be, let's say, when you hydrogenate it. So the hydrogenation of benzene turns out to be less exothermic than would be predicted. Right, by the hydrogenation of 3 double bonds, of 3 pi bonds. Okay, that's enough to get the 2 marks for that. So we'll leave it at that. You could choose other bits of evidence that you'd be familiar with as well. Okay, in part B, we've got benzene being used as starting material for compounds D and E. Here we have D and E, and we've got diagrams of them. And all the question wants us to do is to draw 2 repeat units of polymers that are made out of these monomers. So looking at D, we've got a double bond there. So as usual, what we're going to do is we're just going to draw the carbons of the double bond, all right, with a single bond, and draw the groups that attach to the double bond at right angles instead of at an angle, and like so. And then we're just going to make that the adjoining bond. All right, this part of the double bond is the one that bonds to the next monomer. Okay, so we're just going to repeat that first monomer again, and we're going to have our groups at right angles, and that's our adjoining bond. You can make these, let's just draw it in blue, you can make these dotted lines instead without the brackets if you want, and either one gets you the mark. Okay, looking at E, of course we've got our acid group here and an amine group here, so we're going to make a polyamide. And just because this is not as easy as the addition reaction, we might just draw the adjacent functional groups. All right, so we're going to let's just draw the functional groups, and we're going to have the hydroxyl of the acid and the hydrogen of the amine group dropping out as water. All right, so you're going to get the carbon instead bonded to the nitrogen. All right, so we can draw that out. So the nitrogen is going to be bonded to the next carbon. We're not going to draw that in. All right, it's lost a hydrogen, so it's only got 1 hydrogen left, and it's still bonded to the middle group, which we just draw out as it is. And this is our carbonyl carbon, so it's got its double bond oxygen there, and this is the carbon that bonds to the next monomer's nitrogen. So we can have that repeated. Like so. One more carbonyl, and so that is where we finish it, because it's asked for two repeat units. And there we have that. You'll notice that there's 3 marks, so 1 mark for this, 1 mark for this, and 1 mark for correctly doing the amide link. like so. And to finish this slide off, we've got the type of polymer. So as we've said, this is addition, and this is condensation, like so. If you've put for condensation instead of polyamide, that also is fine. So in part 3, we're going to investigate synthesizing compounds DNE, and in the process we're going to go through this intermediate, which is phenylethanone. And we make phenylethanone by reacting benzene with ethanol chloride, and we need a catalyst, aluminium chloride catalyst. And so the question is asking us about the mechanism, and also how the electrophile behaves. Okay, so first of all, we must describe how we form the electrophile. Okay, so you probably did this in class, but the mechanism, which you don't need to know, is what follows, and then we'll write down the equation, which is all you need to know. But it's easy to remember the equation if you sort of know the mechanism. So let's draw out our ethanol chloride. So we've got our ethanol chloride here, like so, and let's draw out our catalyst. Right, so we've got aluminium chloride. I'm going to draw it like this, like so. Right, and so the chlorine of ethanol chloride is going to attack the aluminium, which still has spare orbitals for that lone pair, and in the process the electrons in the carbon-chlorine bond are going to stay with the chlorine. So then what we get is our electrophile. So the carbon has a +1 formal charge, and the catalyst has changed into AlCl4 with a minus charge because the chlorine took an extra electron with it. So I won't draw aluminium chloride out tetrahedrally. Let's just draw it like that. So a couple of curly arrows in the mechanism there help you remember the equation. So let's just write out the equation. We've got our ethanol chloride right, we've got our catalyst, right, and they go to make our electrophile. Right, we're going to put the positive on the carbon there. You could also put the double bond in there if you want. You don't have to. And we got AlCl4 minus, and we should have a minus on here as well to be strict. Okay, so that's the first mark, all right. But now what we have to do is we have to do the mechanism, and what happens, of course, is the electrons in the ring, even though they're quite stable there, this is a powerful electrophile. So we're going to draw our curly arrow from the ring to the positive carbon, and the arrow must start on the ring, not in the middle of the ring, but on the ring, like so. And then what we get is we get a benzene ring, which is now bonded to this carbon, this and the rest of the extra group there, and we're going to draw in the hydrogen. Right, the hydrogen's always been there, of course, but now we have to draw it because we're going to do something with the electrons in that covalent bond. Now, so we have to. The ring has now been broken, right? So we have to draw the rest of the ring like so, and you have to be careful here to make the ring go past the carbons that are adjacent to the carbon that's made the new bond. Okay, and of course we need our plus charge in the middle because the electrons, the ring has lost an electron, so it's got a plus charge now. And then that doesn't stay like that for very long because the electrons that are in the carbon-hydrogen bond here decide they'd prefer to be remaking the ring. So we're going to draw a curly arrow we're going to draw a curly arrow towards the positive sign of the ring, like so. And so there we have it. So that's the intermediate drawn, and the last thing for us to do is to regenerate our catalyst. So if you remember, we have AlCl4 with a minus charge on it, and that's quite attracted to the hydrogen that has been expelled from the benzene ring, and so that takes a chlorine with it, right, to make a hydrogen chloride molecule, and regenerating the aluminium chloride catalyst, like so. Just to let you know where the 5 marks came from, see how the question is a 5 marker. We get 1 mark for this equation, 1 mark for the curly arrow, another mark for this curly arrow, another mark for the intermediate drawn out correctly, that's 4, and the last mark for the regeneration of the catalyst there. So now we have our phenylethanone, and we need to make it into compounds D and E, each of which is a 2-step synthesis. So let's look at making compound D first. All right, so we start off by reducing it with sodium borohydride. So we reduce it by making hydride ions, which react with our phenylethanone to make this. So we've our methyl group blissfully unaware, but our carbonyl turns into hydroxyl, and we still have our benzene ring. And looking forward to this step here, we have to make this alkene group. All right, so if we could just compare those two molecules, so we have to get rid of this hydroxyl group. We have to make a double bond here, and we have to get rid of one of those hydrogens. So you can see that we're removing a water molecule, making a double bond, which is a dehydration reaction. All right. So what do we need in order to make to do dehydration of a secondary alcohol? We need acid. All right. So you could say H2SO4 acid, you could have said phosphoric acid, you could just say H plus or acid. Any of those get you the mark. Okay, so let's switch back to our phenylethanone and go down this part of the route. So if we look at phenylethanone, of course we've got a ketone, and we see we're going to add cyanide ions, acidified cyanide ions to it. Right, so from a ketone, when we add acidified cyanide ions, we're going to get a hydroxynitrile. So let's draw out the hydroxynitrile that we get. So we've still got our CH3, all right, and we're going to change our hydroxide into a hydroxyl group, and we're going to have cyanide ion on there, and the benzene ring remains. So I just ran out of space there, so we're now going to move over to the right hand side of the screen. So you notice we're going from our hydroxynitrile to a bromonitrile, and so essentially we are substituting out our hydroxyl group from our hydroxynitrile, and we are substituting in a bromine atom. And in order to do that, we're going to need sodium or potassium bromide. And it needs to be acidified. Alright, so that's sufficient to make our bromonitrile. Okay, moving on, we're going to look at how we get the final product. So if we look at our nitrile group here and see what it turns into a carboxylic acid group. All right, so in order to do that, of course, we want hydrolysis. And our acid group is protonated, so it needs to be acid hydrolysis. And the acid that we generally use is dilute hydrochloric acid. We'd also heat under reflux. Alright, so let's draw out what we would get there. Okay, and lastly, we're going to swap out our bromine for an amino group by substitution, and we do that with ammonia in ethanol. Like so, and once we do that, we've got compound E. Okay, question 20. This question is about reaction mechanisms, and we need to explain what does a curly arrow show. And it shows the movement of a pair of electrons. Okay, so with the keyword being pair. Okay, in part 2, if we're looking at this bond here, and we've got the electrons in that bond leaving and staying with the oxygen, then you're going to get a normal water molecule without the plus charge, because the oxygen has taken both the electrons in that bond. But we will have this carbon skeleton where this carbon here has used to have a share of both those electrons in this covalent bond, and now it's got neither, and so the carbon is going to need a +1 formal charge there. So I think the 2 marks are for the plus and for the rest of the skeleton. And in part 3, we want to explain what is meant by heterolytic fission. Okay, so heterolytic means one atom in the bond, one atom in the bond takes both electrons, or 2 electrons. Possibly both would be a better word than 2. Okay, in this case that was our oxygen. All right, and fission means the breaking of a covalent bond. Breaking of the covalent bond there, and in this case, because it does ask you to refer to the mechanism in 2, in this case it was the carbon-oxygen bond. So there we have those 2 marks. So in part B here, we've got an incomplete reaction mechanism, and we've got to add the curly arrows and any missing species. So this would be the missing species here, I guess. Okay, so starting top left, we've got here we've got an acyl chloride, right? So this carbon is going to be delta positive, which means that that lone pair is going to attack it. All right, and that means that this carbon's now got too many bonds, right? So these 2 electrons will jump off and stay with the oxygen temporarily. So then we have this intermediate here, and what you'll notice is that the oxygen here has got an extra electron, and the chlorine here is quite electronegative, as we know, right? So simultaneously, what happens is these electrons are both grabbed or hogged by the chlorine, and this electron dense area decides that actually I'll just share a little bit of a charge cloud with the carbon, right? So they form a new pi bond there, and that results in this carboxylic acid, ethanoic acid. But you'll notice that we've lost that chlorine, and that chlorine is a chloride because it took the 2 electrons in the bond with it. So there we have it. for part 1 and part 2, what is the role of hydroxide in this mechanism? Well, it's attacking a nucleus, of course, so it's a nucleophile. There. Okay, question 21, last question. So we've got some data here. We've got some elemental analysis. We've got an MZ to give us the MR because it's the molecular ion peak. Looks like we've got an IR spectra here, and we've also got a proton spectrum, and it tells us we've got integration values on the peaks. Okay, so we've got to work out a structure for the unknown compound and show all your reasoning. Okay, so first thing, why don't we start off with the elemental analysis. All right, so I'm not going to go through the steps, they're fairly simple. So the empirical formula from that, you're going to get to be C5H6O. C5H6O, right? And the mass, if you just add up 6 times 12, etc., the mass of that is 82. Okay, so the molecular formula, which is very useful, is going to be the MR divided by the, well, it's the MR, which we know is 164, divided by the mass of the empirical formula, which is 82, times our empirical formula, which is C5H6O, of course. So that's going to give us 2 times that, which is C10H12O2. Right, so we've got the molecular formula. And if we look at the IR spectrum, we can see we've got this broad peak, which is indicative of a hydroxyl group of a carboxylic acid, and we've got this peak here at about 1700, which is our carbonyl group of the carboxylic acid. All right, so we could write broad peak at about 3000 and sharp peak at about 1700 indicate carboxylic acid. So next, if we look at our proton spectrum, so we see we've got heavy water, we've got deuterated water, so any acidic proton is not going to be there. Right, so we know it's a carboxylic acid, so one of our hydrogens is not going to show a peak. And so let's just add up the integral numbers. We've got 4, 5, 6, 7, 8, 9, 10, 11, plus our missing one is 12. Right, so we know that the integral numbers correspond to the number of hydrogens. So therefore we can say that if we're looking at this peak at about 7.1 or 2, that corresponds to the hydrogens on a benzene ring. All right, so it means we've got 4 hydrogens on a benzene ring. So let's write out that in a way that would get us the marks. So we'll do a little subtitle. So we're going to talk about the peak that's at sigma equals 7.1 to call it 7.4. Right, and the points we can say about that is a multiplet, as usual. Right, we can say that there are 4 hydrogens on a benzene ring, so we've got C6H4. Moving on to the next peak, so that's let's call it the peak that's at sigma equals 3.4. Little subtitle, Okay, so it's got integral of 1. All right, so it's CH. It's a quartet, so it's next to CH3. All right, it's got a shift of shift is, we're reading shift 2.7, of course. Right, so the shift of 2.7 means it's also next to a CO. Alright, so we're going to put that information together, and we're going to get our CH next to a CH3, also next to a CO. It's probably the CO of our acid group, so I've just drawn it at that angle just now. So let's leave it at that just now, because that's all the information we can get from that peak. And let's move on to the next peak. On your exam paper you've got more space, so I'm getting a bit squashed here. So let's work up here. Next one is a shift of 2.3. So we're going to read this peak now. So this has an integral of 3. Right, it's got an integral of 3, so it's a CH3. And right, it's a singlet. Alright, so no adjacent hydrogens. And its shift is 2.3 or 4. Shift equals 2.3 or 4, right? So that also tells you that it's that these are the hydrogens on the benzene ring. So it's next to a benzene ring, rather. It's the CH3 that's on a benzene ring. Right, and let's just draw what we've got there. The CH3 coming off it. Okay, so that's read those 3 peaks. Let's read our last peak. That's at shift 1.6. Let's do it over here. So shift equals 1.6. And as usual, do the integral first. So the integral is 3. Right, so we're going to guess that that's those hydrogens on a CH3 group. It's a doublet. It's a doublet, so it's next to a CH. And we can conclude from that it's the CH3 that we identified earlier on. So let's draw it in the same way. This is the CH3 that we just worked out, like so. So I'll switch colour to green, so you might not write this down, you might just think it. Right, so we get to the place where we've read all our information, we just need to construct our molecule from all the little pieces. So let's first have a look at this and decide where that's going to go. I think what we're going to do is we're going to put that on here, right? So that's going to go on there with a CH3, right? We don't know what carbon that's CH, that methyl group is substitute onto, right? But it won't matter. These 4 hydrogens are the 4 hydrogens on the benzene ring, and I think if we just go up to the top and look at, remind ourselves that we've got a hydrogen, an acidic proton that's not got a peak, all right? So we're going to put that here, right? And we know from the infrared spectrum that we're going to have a carbonyl, which is this one here. Always good to write that. So the carbonyl can go here, like so. And that's a complete molecule. All right, so let's switch back to red and draw our complete molecule. I've run out of space, so I'm going to do it up on the proton spectrum. So we've got like so, and we're going to just do our final check. So that's our proposal for our final molecule. And what we can do is we're just going to refer back from all the hydrogens on the molecule to the peaks. So let's just do that. So you wouldn't necessarily write in your exam script in this way, but just to do our final check. Let's think about these 4 hydrogens here. They're the 4 hydrogens that we've got hanging off our benzene ring. 1, 2, 3, 4. So we like that. Now let's look at this one hydrogen that is a quartet. Right? We think that is this one here. These 3 hydrogens here that have no adjacent hydrogen, right? They must be this peak here. So that's all good so far. And these 3 hydrogens that have just one adjacent hydrogen, that's these 3 hydrogens here. Right, so that's nearly everything accounted for except for our acidic proton, right, which doesn't appear because we're doing it in heavy water. So it makes sense. And there you have it, that's worth your 6 marks.